Hello everyone, and welcome to another edition of Compiler, the stream in which we try to solve bugs in SpiderMonkey in a single episode, and it turns into 6. That takes more than a month. Welcome. We are going to be diving deeper into stuff I don't know about. Namely, we're going to be looking more at the JITs. So I've been working primarily on the front end. The JITs are new to me, but we're going to see what we can learn about it together anyway. And this is going to be the last stream that will be following the current schedule. So, so far we've been doing a weekly stream where I come on here and hack on the SpiderMonkey bug that we've been working on. Next week will be, so not next week, but the week after next week will be TC39, and I will need time to prepare. We tried the TC39 episode last time, and it wasn't 100% what I wanted it to be, and I think it would be too much for me to try and do it again, because the preparation for these streams actually takes quite a bit of time. So there will be no stream for the next 3 weeks, and we'll be resuming 3 weeks from now, and I can't quite remember the date. Maybe I can look it up. Well, I'll post a link to the date when this resumes. And that actually brings us to a crossroads, because we can decide once we're finished this episode if we want to continue working on this bug, because we're going to get to the point where we have fully implemented the bug that we were working on to all the way up to IonMonkey. But we won't have done any of the optimization work. We're going to skip over something called Inline Caches, which is quite important and is required for this feature. But we're just going to get to the end point. And in 3 weeks, we can decide if we want to continue with the same bug that we've been working on, or if we want to start a new cycle and start at the beginning again. So that means we're going to start with a new bug from test 262, identify it, implement it in the front end. Then we're going to, if it requires it, implement it in the JITs, and then we're going to continue that way. So that's 2 options that we have. You can inform me in any way you like. In fact, I've now created a space online for us. It's been very quickly made, so there's a little bit of work to do. I've created a space for anyone who's watching this stream and wants to participate in the stream. And I'm going to show you that now. Specifically, we now have a repository called compiler-compiler-dev. It's off of my GitHub. And what it is it's a copy of Gecko Dev. Gecko is our browser engine. SpiderMonkey and Gecko live sort of together. SpiderMonkey is part of the browser. And this is a full clone of that. And what the goal of this is, so if you just go to the master branch, there's a tiny README that will tell you everything you need to know. Also, we've got a logo, by the way. We'll tell you everything you need to know in order to build. So if you follow the instructions, you can build SpiderMonkey for yourself. If you have problems and you don't know where to ask, and maybe you don't know how to set up Riot and you just want a place to get started, what you can do is you can open an issue. Wait, where are the issues? Oh no, I'll figure this out. Apparently if I make a branch, it doesn't make issues. I haven't done that before. I will make it so that it works so that you can post issues here, and you can ask questions, and you can get feedback directly from me in an asynchronous way, in a way that's more formal than Twitter. And namely, what's going to be happening now is you'll be able to search this repository for branches that start with a bug. This is the bug we've been working on for the last 6 weeks. And there will be information in these that'll tell you what you need to know in order to reproduce the bug, which test 262 test is the one that we started from, which episodes you need to watch in order to have all of the groundwork for what's been going on, a quick description of how to reproduce the issue and what the core issue is. It's basically the same thing as the test, but done in plain text. How to build, and then how to run one of the tests that's failing, just to get you started, just to get you thinking about, like, how do we look at this bug from the perspective of writing an engine. Then, if you want, you can go and start implementing yourself and solving the problem on your own, Or if you need a place to start and you just want a refresher of the streams, but you don't want to watch the streams, all of the patches that we've done are now available for you to review and to see the changes. So from our very first episode, when we implemented the naive fix using 2 opcodes, that would one opcode to swap so that we could get the check object coercible, and then to swap back, and the tests that were fixed and everything that you need to know for that very first stream, it's here, as are all of the other streams, including if I had to do corrections. So for example, in our last stream, I needed to correct the baseline implementation. You might have noticed I was surprised that it worked, because I had expected it to fail, because I wanted to show you something about it failing. And if we have time at the end of this stream, I will show you that failure, and we can talk about it and get some more information. But effectively, this is going to be a place where you can go see everything just as diffs to the code base, and then take either inspiration from it, or you can do something that I did rather early in my career, which is tracing, copying a diff line by line and trying to understand it just by copying it. Many of you might know that I formerly was an artist. Well, I guess I kind of still am. And the way that I learned how to draw realistically was through tracing. And the thing about tracing is that it allows your mind to relax as you do the mechanical action, and that can allow you to learn quite a lot. So don't feel like there isn't anything to be gained just by copying a diff. There is a lot to be gained from that, especially with the streams that explain to you everything you need to know about what we're doing here. Is there to do? Is it in the to-do to talk about IonMonkey optimizations in the future? Right, so we're going to be taking a break for 3 weeks to accommodate TC39, the standardization committee for JavaScript, which I'm a part of, and I've got prep work to do for that. So we're skipping for 3 weeks, and if we want, we can do optimizations 3 weeks from now, if that's what you're most interested in. Or we can start a new bug, because we do have a list of bugs that we can continue with. So that is up to you. I will set up a way to poll for this, and you can give me your thoughts about what you would rather hear. Lampel2 asks, what is tracing? Tracing, what I'm using to refer to as tracing is like literally you start with this patch, like you would start with the very first patch, the initial implementation. You would read it and say, okay, this modifies element operator emitter, and it does a few changes, and we changed the test list. What you would do is you would go step by step and see what happens as you make each change. So you would, for example, remove this call and see, you would recompile, see what happens, try to learn what's breaking, what's changing, implement the next step. Again, run the code, see what happens, see what changes. And the tests are obviously not going to be executed code, so this isn't as crucial for tracing. But basically, it's a guided way of copying the code that you see and trying to understand what it's doing. So you should feel free to do that and see what you learn from it. All right. Are there any other questions before I review what we've done in the previous stream, so that we can start with the IonMonkey implementation? I'm going to give it a second. So think about the questions. I'm just going to quickly review our previous implementation. Let me just see if this is big enough. This text is tiny, isn't it? Let's make that bigger. Okay, so what we did in our last implementation is we did a version of this that works for the baseline compiler. Now, SpiderMonkey is composed of multiple compilers, so you can think of it this way. We have an interpreter, which last time we described as something that is a giant for loop, because that's what they are, that has a lot of case statements in it. And for each opcode, we start at the beginning of the for loop, find that opcode, execute that bit of code, and then like loop back to the top, find the next one, loop back to the top, find the next one, etc. So we're always jumping to the head of the loop and then finding the thing that we're working on, executing it, and then going back up. The difference between an interpreter and a compiler is that a compiler doesn't do this looping. Instead, what it does is that you can think of it as a specialized interpreter that takes all of the instructions that you would have hit for that set of bytecodes, and it executes them inline, like one after the other, rather than looping through and finding each one. And the bug that I had intended to show you was actually to show you where that script lived. We can take a look at that. So what we have here is a bit of code in the baseline code gen, and the baseline code gen is shared between the baseline compiler and the baseline interpreter. If you recall, we made this super tiny engine last time to explain how an engine like this works, where we have again, super tiny text, where we have the interpreter, which is a for loop, and then we have a compiler which shares the same code as the interpreter. The instruction set is shared. But instead of going through this switch every time that we see that opcode, what we're doing is we're compiling all of the instructions that would have been executed by this into a single script. And then if we come across something that has the same ID or some identifier of some sort, we will run the script instead of going through running it manually using the interpreter. So please ask questions. Tell me to slow down if I'm going too fast, and I'll be super happy to cover anything. Okay, so what we're doing here is an implementation that covers both the baseline interpreter, which works as an interpreter, giant for loop, and a compiler. The compiler also uses this code. So someone is asking about the IronMonkey optimization. This question is already getting into the topic of optimization, and there are two things here. One is that we won't have time in this stream to cover it, but we can cover it in the next one. The second is I haven't had enough time myself to learn it, though I will show you some ways of identifying what's happening in IronMonkey. And yes, Ian is one of our experts on the JIT. He actually helped me put this episode together, so he'll be able to answer that. For the question about are there recordings for this series available anywhere? Yes, there are. You'll actually be able to find it in this repository that I've now made, and also on Hacks. It is basically this YouTube playlist. We're a little bit behind on transcribing them, but you'll find all of the previous episodes here. I'll just drop that into the chat so that you can have it. Okay, so let's get started with how do we get Ion set up to interpret this bytecode? Because the current state is that Ion doesn't understand the bytecode. All right. Well, let's just jump right in. What do I have here? Nothing important. Okay. So in a previous stream, we actually turned off Ion. Let's actually take a look at how we turned it off. I think we turned it off here, did we? No, it was a previous one. Let's look at implementing the bytecode in the interpreter. Should have had them all loaded up already. Okay, let's see. Here we have the definition for the opcodes. Okay, no, I actually remember where it is. I'm just going to show it to you, and you can look at the diffs yourselves. It won't be too difficult. Oh. There we are. Really? Where am I? Someone asks, what am I working on? I am working on SpiderMonkey, which is the JavaScript implementation on Firefox. And what I'm doing is I'm fixing a bug, just to give you a super fast idea. Let me open a new tab. Okay, so for example, if you have some object foo and you want to access hello on it, and then you increment it. This is an important point. If you increment it, then what happens is it evaluates this expression, this whole expression, differently than if we do this. So the difference of adding this increment operator means that we evaluate whether or not this foo exists before we evaluate this argument, which is different than if we don't have that increment operator, where we will evaluate this first and then this will be checked if it's null or not. DevSnack is asking, does Ion handle IC feedback? I'm not too sure what feedback means in this case, but I believe Ion does use, no, I know that Ion uses the IC. IC is inline caches. And I believe it compiles its own inline caches, while the baseline compiler also compiles its own inline caches. An inline cache, we're not going to go into depth about it, but an inline cache is essentially, let's say, it's an optimization that was made for dynamic languages, I believe from Smalltalk, if I remember correctly. What it does is, let's say you're running some code and you need to do a lookup, like a property lookup. And a property lookup is really expensive because you need to do a lot of work in order to do that. What an inline cache does in that case, and there are multiple kinds of inline caches, this is just one. An inline cache will record the result of that lookup so that the next time that you hit this and it's the same thing, you don't do that round trip, you just have the value there. And the question about my IDE, I am just using a terminal with Vim. The reason that I don't keep it in dark mode is for presentation purposes, it's easier to read when it's a white background than when it's a black background, especially if you're projecting. So I just, my default setting is for presentation. So I just got used to it. Why does it evaluate the expressions differently, and why doesn't it check the value first before it can increment it? That's a great question. We cover it in a previous stream, so I would recommend watching the very first stream where we go into what the code is doing and what it was doing wrong and why it needs to be changed, because what we have to follow the JavaScript specification. So if you haven't seen it yet, this is the JavaScript specification. And the very first episode goes into reading the specification and understanding what instructions it's giving us for how things should be evaluated. And that's where the bug comes from. So most of the bugs that we're going to cover here are going to be related to the specification and ensuring that we are as close to the JavaScript specification and web compatibility with other browsers as possible. That's the goal. Okay, coming back to Ion and getting this working on Ion. What was I doing? I was doing something. Oh no. I guess, oh right, I wanted to check if I was in the right place, because I expected there to be something else here. So I expected that when we were in Ion Builder, was it here? Let me take a look. I might just be looking in the wrong spot. Yes, I'm looking in the wrong spot, that's why. It's not in the header file, it is in the body. So we're going to ionbuilder.cpp, and we're going to look at how prepare element was being handled. We have it turned off in IonMonkey right now. Someone asks, what organization makes the JavaScript specs? Is it an ISO? I believe ISO is an International Standards Organization. ISO is a very specific standards body. The standards body that covers JavaScript is ECMA International, which used to stand for European Computer Manufacturers Association. So that's where the name ECMAScript comes from. Legally speaking, the trademark Java belongs to Oracle, so we can't actually call it JavaScript. So we call it ECMAScript because nobody could come up with a good name. I personally think that we should have called it OakScript because Java's previous name was Oak, and I was like, let's just take their old name. But yeah, whatever. So yeah, the organization is ECMA. And if you want the full name of JavaScript, it is in fact European Computer Manufacturers Association script, because we are the only thing that is trademarked by ECMA that still uses all uppercase letters, which means it's still an acronym. Ha! Okay, so shall we turn this on for Ion? I think we should. Let's see. This stress is real. DevSnack says that they are surprised that we put specifying JavaScript in the homepage. Yeah, we did, because the split of naming is difficult for people to learn, and colloquially it's been known as JavaScript for so long that we want to make it easier for people to access the specification, know where it is, know what it is, and follow it. That page is also out of date. If anybody wants to help me keep the website up to date, because I also do that, I would love that. You can open an issue and I would be the happiest person if people help me keep that webpage up to date. Okay. So what I just did is I removed prepare set element from this warning, do you really want to sacrifice performance by not implementing this operation in an optimizing compiler? And we did at the time. And actually, we're not going to gain any performance. We're probably going to lose performance when we do this because we're going to be we're not going to be running any optimization steps, and you'll see that in a second. But well, not in a second, maybe in half an hour. Okay, I'm going to move a little faster because we are almost halfway through the stream. So I want to put our implementation next to toPropertyKey. And that is here. And I'm going to do a little bit of magic aside from renaming stuff. So I just added some renamings, and I added a case for something that doesn't exist yet. And I'm actually going to add one other thing, and I'm not going to explain it. This is just to get it to work. It's not correct. As I said, we're not doing a correct implementation. We're doing a full implementation, but it's not going to be right. Also, there's no IC, which we should have in this case, and other things. This is a really sensitive piece of code that is performance sensitive. So we are breaking that performance sensitive aspect, which is why this isn't going to be merged. We'll see how far we get with this. Okay, so we now have prepare set element put in this magical place that I'm not going to explain. And then we go to property key again. Let's find it over here. This is going to go really fast from this point. I'm terribly sorry. Please tell me if you don't understand something. I just copied over toPropertyKey because prepare set element consists of two other bytecodes. It consists of check object coercible and toPropertyKey. So I just copied toPropertyKey and just put it at the top, and I'm going to rename it. But we'll be doing something very similar to what toPropertyKey does. And I'm going to add this also to the header file. So this isn't, this is just stuff to make it work, because we're doing it in C++. Okay. So cool, we've got a tiny skeleton for how this is going to work. Someone asks if Chrome engine uses the ECMA standard or their own thing. They use the ECMA standard. All engines implement the ECMA standard to varying degrees of correctness. All right. Okay, let's talk about what the old toPropertyKey was doing. So what we have here is something called a mirror type. And we have this object called current that has a private method peek, and we're peeking backwards. And then we're getting the type from that. So we're peeking backwards and checking the type of the thing that's behind us. Then, depending on what that type is, we are going to exit out early and be like, we don't need to do any more work here. And then, next, if we do need to do more work, again, we're doing toProperty key. So the operation we're looking at is, let's take foo again. We've got some string that we're accessing dynamically inside of foo. This is the case, and we're looking at this bit. What's happening is we're going to transform that into something like this. Like you can imagine it as we're going to do a property access like this. There's more complexity here. We actually have on the front end the ability to make this transformation. And this isn't the actual transformation that we're doing, but you can just think of it like foo now knows where this string key is in terms of its map of objects. Right. So we peek here, and peek sounds like we're just looking, right? And then next thing that we do is we pop. So that's exactly what it sounds like. In one case, we have you can think of it as a list. You can think of it as a list where you've got opcode, opcode, opcode. And this opcode, we know what it is. It's prepare set element. So we're here. And when we say to peek -1, we are looking here. So the previous opcode, this one. And then we say, okay, that's cool. I want to pop that thing that was before. So we're actually more like looking at a data structure that looks like this. And we say that we want to pop something. Oops. We're going to do that and just pop it off the stack. So that's what's happening here. And we assign it to index. Then we have this thing called toProperty cache, and it comes back as ins. What is all of that? We're going to find that out later. First, we're going to implement with the existing mirror graph nodes, I guess it would be called, and then we'll implement our own mirror graph nodes. That's why we have to go super fast. And then the next step that we do is we push something here. So current pushes back the stuff. And then we do a resume. So some details there, but this should give you a general picture of the data structure that we're operating on and the set of steps that we're taking. So at the moment, prepare set element is doing exactly what toProperty key does. I'm going to remove the pseudo stuff. And let's take another look at what our definition in the opcode was. How far back is it? It's probably really far back. Oh no. Is it in front end? No. It's probably in VM. There we go. So here is our macro definition of prepare set element, which we did 2 episodes ago I read the chat and now I'm thrown off. When we implemented it for the interpreter. So that's 3 episodes ago if you want to check out that episode. And what we have here is it tells us a bit of information about what this opcode expects and what the different compilers implement for it. So we have a stack of 2 elements, an object and a property name element, a property name value. And then we return 2 elements, that same object and the property key. Just going to see what's going on in the chat for a second. Out of band. Yes, that's more about JIT compilers. There isn't an ISO spec for JavaScript, as far as I know, because there is only one standardizing body for JavaScript. Unless ISO has some layering stuff. I'm actually not too sure if we have any interactions with ISO. Oh, ISO republishes. Thank you, DevSnack. Yes, that makes sense. ISO republishes ECMA 262, but the standard is done in TC39. Okay. What was I doing? Right. So what I just showed is we have two things on the stack, and at the moment we're operating on something very different. What we're doing right now looks more like this. And we don't want to do that. We want to do the other thing, which means that we need to take into account the other opcode. And that opcode was check object coercible, which looks like this. And I'm just going to copy pasta everything. And I'm just going to have it at the top, and we're going to pull stuff in as we go and then rearrange the code as necessary. So we want to check -1 for the object, but let's actually also copy over what our stack looks like. So we are somewhere here. This is where current is. And property name value is -1. But to check, which is this one, and this is going to be index, to check is 2 back. So in order to get that, we need to modify this to -2, which means that, actually, we can just do this. Okay, so now it's still consistent. Now we're getting the right element, because before, if we ran this on the code, we would be checking the name value if it's to object coercible. Wait, I just went completely bonkers and backwards. It should be -1 because this is index. And to check is -2. There we go. Thinking on my feet. And what you see here is we have to check is being checked if it might be 2 types of mirror type. The first one is undefined and the second one is null. If it's either of these things, we will say set implicitly used unchecked. I'm not going to go into what this does, but it helps us make sure that we're doing the right thing. And I'm going to just grab that because this is what we want to do when we are doing this to check step. So we're focusing on the to check step. So if it is either one of these things, then our condition, which is make sure that we don't have null, like whatever, if it's null, we should go around this. But if it's not null and it's some value, foo, then what we want to do is whatever the happy path is for foo. I do have a link to my config files. You can find it in my GitHub repository. I think it's really out of date because I only updated it when I switched computers, so it might be like a year or 2 out of date. Okay, and then there's a discussion about ion. Okay, so this is the happy path. Now, if we return OK right away, then we're not going to be doing the step that we need to do, which is to identify whether we need to figure out what the property key is. So let's understand what this code is doing a bit better. What this is saying is, if it's an int or a string or a symbol, return OK. So actually, this is also the happy path. We can return early because we can access those directly. The comment here says it's a no-op if the index is trivially accessible, convertible to a property key. So this is also the happy path. And we only really want to do that if the code is nice. And there are some other things we can do to make this better, but in the interest of time, I'm going to skip ahead to going into the sad path where one of these checks fails. So that's something like this, or it's something like this. So both of these cases, only this case is the happy path, which will exit out here, and then otherwise we're going to do something else down here. Okay, so Here is the code being angry and really unhappy with the situation. I'm just going to dump it. Now, there's a comment here about squeezing out more performance. We're actually not going to be getting any real performance from this, but we're going to follow the structure of the code, just so that when you come to it, you can see how this was built by putting the pieces together yourself. Now, right now, we have a check for... Oh, wait, there's one other thing. I did this wrong. This should also be part of the happy path, because we should only call this code if things are as we expect them to be, like happy lines. So if you recall, I started the code with a toProperty key, and I just moved all of toProperty keys implementation into the top part of the function, where toCheck is either not undefined and not null. So that's the good times. Okay, and then the rest of it is as it was. There is one error here, namely that what we have here is we are doing current pop. Recall that the data structure that we're working with is like this. And the pop would pop this index, and that's the wrong thing to operate on. It can do the operation on that, but that would be the wrong thing to operate on. The right thing to operate on is toCheck. So we need to get toCheck out of there in order to be able to run it. So in the interest of time, I'm just gonna grab this. There was a way to do this. Push slot. I don't know if this is going to be the prettiest thing. Is this a bad idea? I think this is a really bad idea. We're just going to do something really dumb because we're going to fix it later. So I'm just going to grab that and be like, do this thing, even though we don't actually want that toProperty cache key, it's wrong, but just to get it to the point that it works, then we do that. And the check should go first, so we're reconstructing the thing. There we go. So we start off with this, we pop, that means we pop this item. Then we get here, which means we've popped this item. Then we get here, we've pushed check. And then here we've pushed index. So, any questions so far? Yeah. Okay, cool. So this is kind of working, but it's not really what we want to do. This is making Ion work by translating the opcode the opcode prepare set element into two other opcodes. But ultimately, we actually want to implement this all the way down. So we're gonna implement the mirror node for it. Mirror opcode, I guess, is the right word. There are words. Okay, let's do that. Let's start with mirror. Okay, so I'm going to do something very similar here. I'm just going to start with property key, dump it. Check object coercible, grab it. Property key cache. Also, this is toProperty key cache, you might have noticed, because this is relying on caching, but whatever. Okay, so we have these two functions. I'm going to continue modifying the property key cache. And it is prepare set lm. Wait, is that right? Yeah. Okay, cool. Now, this is, again, not what we actually want, not quite the implementation that we want, because it's a unary instruction, meaning it takes one argument and it outputs one thing. And it's got these annotations to tell us to ensure that the graph that we build is correct. And a box policy essentially tells us we don't really know what this thing is. So the types that we've been working at is it could be null, it could be an object, it could be a function, it could be anything. So box policy makes a lot of sense here. But now we need to get that second argument, because again, we've only got one argument in here and we need two. So I'm going to grab this and I'm going to copy it. And oops. I'm going to name it checkVal. Let me make sure that I'm on track. Yes. Let's make sure I am on track so that I don't lead you astray. Okay, so first thing to change, we have a unary instruction, which means that prepare set element is currently taking just input. So you can imagine it as a function and it returns output. Not what we want. We want to change this into input and, well, actually, we want to change it to check object and input. So in order to do that, this has to change. And we have an instruction for that, which is binary instruction. And oops. So now it's, why are these files so big? I am live coding IonMonkey. Yes. Why are these files so big? Because of life. I think it's partially legacy, partially not splitting it up into a million files, and it might be partially performance. And JS is very complicated. Okay, cool. Now the next thing that we need is mixed policy. Mixed policy allows us to pass two things in. I'm just going to copy that. And then we've got the box policy again. And both things that we want are box policies. We can verify this by taking a look at what toProperty cache used and what checkObject coercible used. So here we've got box policy, and here we've got box inputs policy. We're going to use box policy for both of them. So I'm going to dump this bit. Cheers, box policy. Yeah. More or less. And what else do I need to do here? We have input. We need check. I think to check was what I used. Okay. What did I need to do else here? Did I need to do anything else? Aside from naming some operands. So we have 0 is check value and 1 is input. Is that right? I think so. I think that's right. More or less. It might be wrong. I don't normally work on the JITs. So this is, your guess is as good as mine. Let's put it that way. Okay, cool. That should do it for mir. And now I'm going to switch over to LIR, lower intermediate representation. So this is mid-level intermediate representation, and we're going to go to lower level intermediate representation. These are both graphs. The distinguishing feature between mid-level and low-level is low-level allocates registers. Once we have this running, I will show you exactly what that means. I have such fear that this will actually not work. Okay. to property key cache. And you know what? We're going to be doing a lot of the same thing because we are just merging two keys together, and we're going to use the exact same building blocks. So what am I trying to do? Check. Okay, here we go. 1 second, I'm just going to make sure that I didn't mess anything up here. But I did. Look at what I messed up. I left a second definition of check object coercible. And now we just have our prepare set element, which is the code that we added. And here we have double to property cache key and then check object coercible that I'm just using for reference. And we're going L prepare set lm. Cool. It looks pretty good. No big questions for me, I think. Okay. So I'm just going to keep implementing the bits. So again, we have two inputs here. I think that this needs double const. Let me see if I remember the convention. Yeah. This is to property cache key. This is supposed to be wait, what was that? There we go. Copy paste. That is the life. This is still input, and this is now check value. Is that right? I think that's right. Well, there it's value. I'll just follow what I did before. Okay, so the first argument looks exactly the same as the argument that's here, and the second argument looks exactly like the argument that's going for to property cache. And there is one change that we need to do, which is this box pieces tells us about the size of things. So box pieces, we're dealing with boxes because these are unknown sized values, so they could have a variable size. So we can't say 0 or 1. We have to deal with something that is held in this constant box pieces. And I'm having a hard time because I'm trying to find my notes from before. Let's see if I can find them. Oh, I have to press enter. There we go. Am I doing everything right? Yes, looks good. Okay, so let's talk a little bit about that stack and what's happening on the stack. Was there a question for me? Okay, lots of questions, but none for me, so I will just keep going. Okay, so we're starting off with check value and input, or the key string. And this is being transformed into check value is unchanged, but the next thing is a key. That's the thing that's going to change. So if we look at the L instruction helper, can I find the definition quickly? Probably not. Well, how about I just do it using something more useful. Let's go to the spec. So for people who are new to the stream, we've got this thing called SearchFox, and it's a super fast way to search the code base to find whatever you're looking for. And we were hanging out in lir shared.h, I think it was. And what we want to know is what does L instruction helper actually do? You can click on it and it'll take you directly to the definition. It's a template that takes a set of definitions, a set of operands, things that it works with, and a set of temporary variables. Based on that information, we can decide what we need to implement here. So what did I just do? Okay, there we go. Based on that info, we can say that this check value stays the same, but this key gets defined. So we have one defined box value. However, the number of operands that we operate on is 2, because we have these 2 operands. So what we can do is we can say 2 times, that's an at, 2, times box pieces for the number of operands that we use. And in terms of box pieces that get defined, that's 1. That's why it just stays 1. Next, that means that, so we've got these 2 constant integers here. And what they represent is where you find the information we're gonna place. So what we're doing here is we're setting the box operand, but we need to have a location, and these are constants that we're using to name them. And in this case, what we want is to name it box pieces, because it needs to be offset a certain amount because of the size of the objects that we're allocating. Did I need to do anything else? Yes. Oh, the fun bit. Okay. So then we need to be able to access those. And we can get operand, and again, we're using the same constants. This time check value. Was there anything else? Yes, this needs to change. I think it's supposed to be prepare set 2. Okay. Sweet, we're totally going to go over on the stream again. There's no way I'm going to get through everything in this stream. This is why we're not doing Cache IR, because it would be a whole other hour. Okay. We have an implementation of the lower instruction level, and we're telling it how big the pieces are that we need to be allocated, so that when we get ready to do the registers, we'll be able to do that. Okay, so there's a really great question from one person saying, what's a good starting point to learn C++ for a JS developer? So full disclosure, I did not know C++ when I started working on SpiderMonkey. I wouldn't say that I knew it. I had worked with it in the past, but very limited, and I had a really traumatic experience because I tried to program printers in Windows, and I never touched C++ after that. So my experience was limited at best. However, switching to SpiderMonkey, it was super friendly because SpiderMonkey is written in an opinionated way. So it's not as easy to make strange mistakes like what I was doing with the printer code in SpiderMonkey. So for JS developers, it's actually super friendly as long as you sort of get used to seeing things that maybe are segmentation faults, but don't get too nervous about them. Throw in a couple of print statements, learn how to use a good debugger, and you're on your way. So line 787 should be a different type. That is correct. Thank you, Ian, for saving this entire live demo that I'm doing here. Okay, cool. And everything looks like maybe it's going to be happy. I do have a backup in case everything goes wrong. I think we're good. Let's move on to, let's just make sure that I delete stuff that's not supposed to be there. So here's a reference, it's going to disappear. And we have an implementation in Lear. That's it. Now we need to actually implement it working, which is another story. Let's open a new tab, and I will open, what do I want to open? What did I do? Well, I know that we need to do lowering.cpp, so let's do that. Where are you? Boom. So now we need to implement the exact same thing, but in the lower, Lear thing. Oh, code generator. That's the one that I should start with. Thank you. Code generator is totally the place to be, and I passed it. There we go. To property key. Not cache kind. We're not interested in caches. Visit this thing. Let's do it. And this is going to get super, super fast. Once again, same pattern that we followed before. We're just implementing the same thing like 10 times. That's what's happening in this stream. Right, prepare, set. I didn't rename it yet, so to property. And I'm gonna get the cache again. Cool, I should really be commenting these out because that'll be safer. There we go. Okay, so now this mirror is a graph, and we are traversing the graph and visiting the nodes. This is the function that we call when we visit a node. I should really learn how to use the Vim shortcut for renaming things quickly. Eventually. Everything at good time. Okay. Okay, and we are for sure not using the IC. Cool. So once again, we're starting with the property key cache implementation. That's not what we're going to want to use. In fact, looking at this code, we're not going to use any of it, so goodbye to that. Cheers. Let's grab this code. Actually, I'm just going to leave that there for reference, just in case. Okay, so the first step that this is doing is it's taking from that lowered representation the check value, and then it's creating this template function. And if you recall, we did the same step in the baseline compiler. This looks exactly like baseline. Baseline. Oh, this isn't right. Baseline code gen. So let's take a look at that. Prepare, set. Okay. Remember this? We're doing that again. That's exactly what we're doing, and we're going to even reuse the same functions, because what we're doing when we do call VM, we're using something called a trampoline. I didn't talk about it in the last stream, but that's what we're using, and what it's doing is it's setting us up, like you jump onto the trampoline, and it sets us up to make a call into the C++ code. So we're relying entirely on the C++ implementation here. So going from the JIT up. And we're going to use the exact same functions that we used here. So the first function we're going to use is this one, throw object coercible property key, and then the second one is to property key operation. Exact same thing from last stream. What am I doing? Check value input. And I will rename these ins to lir. In this case, it's JIT, but I guess you could call it, git JIT, just like git, GIF can be GIF, which is a reality we have to deal with in English. Okay, cool. So we have stuff happening. So we've loaded the check value from the lir object, where we said 0 points to this, and the offset with the box pieces points to this thing, which is the input, which I misspelled. Input. So we've got those 2 bits, and now we want to work on them. So the first piece of work that we're doing is using an out-of-line code. We could use something else here, but there's another form that we can use here, which is actually specifically this one. But I'm going to use that for the next piece. For our purposes, it's not really a make or break situation. This code is going to work. That doesn't mean it's going to be correct, but we're going to get it to work. This is going to be function 2, and instead of doing create async, I'm going to just grab the thing that we used in baseline. There's another difference here. So actually, I'm just going to use this. It's the exact same. Signature as what we used before. So I'm even just going to, just to drive home that we're doing the same thing as baseline, I'm going to copy the code from baseline. And again, we're not using anything like, we're not using any optimization techniques. We're not using any inline caches, anything. We're just getting the pieces in place in IronMonkey so that in a future episode, we can do optimizations and then do this correctly. So check value and input. And I believe that is everything we need. Let me check. Yes, that's what I'm looking for. Ah, yes, I'm missing one crucial bit, one really, really important bit, which is I need to push the argument that we're using, because otherwise it's not available. And there was one other thing, which is I think I didn't fully finish this. But you know, let's even see if this works. This might not work, but if it doesn't, then I've got backup code to make sure that it does work. Because I was doing a bit of debugging and I couldn't figure out why my values were being reversed, and I had a really great debugging session with somebody. I can show you that debugging session because we have a really cool way of doing that. Okay, more or less works. Let's get rid of this. So this covers inside of the code generator, and now we want to cover the lowering code. So when we're going from the mirror graph to the Lear graph, that's the last piece that we need to do, and then we need to correct our implementation inside of IronMonkey to use this infrastructure that we've built. Lowering. Here we are. Okay, same deal. We have a graph and we have nodes in the graph. When we visit one of those nodes, depending on the type, we call one of these visit functions, and then we do some work there. So this is going to be visit. And same basic situation here. Just making sure I've got everything in place. Same deal. We have this input, and I made a mistake here, and we can see that mistake. It's fabulously broken if I do it the way that I did it originally. But we can do check val. This doesn't need to be get operand. This needs to be was it check? Is that what it was? Check value. I can see that if I go back to here, check val. So it's this. Oh, I just confused myself horribly. Okay, here we are. And input is input. And here, I think, I can't remember. That should be also fine. I don't think we need to change that. Here we are translating it into the thing that we actually want. Wait a second. Let me make sure that I'm using all the same names, because this one's check value and we're actually going from mir. So what I just wrote was incorrectly because I was using Lear. But to avoid that, I will just name that check value. And that should solve that problem. I have this doing something different. I don't know if this will make a problem. I'm just going to leave it as it is. And if it makes a problem, then we'll solve it. Oh yeah, I did something wrong. This shouldn't be like this. Because we're using a box, we're putting stuff into a box. It doesn't take 2 arguments. And we want to redefine. So here we're defining this. I don't know if this is actually necessary, but I'm going to put it there anyway, and if it's not, we'll deal with it later. Okay, cool. That covers doing the mirror graph node definition and its visitor, and the Lear graph node and its visitor. I believe this one is for mirror, and then the other one is for Lear. Okay. So, coming back to Ion Builder, the thing that we were working on earlier, that we started off with a partial implementation but not a full implementation. Now we can do an implementation with the mirror and Lear stuff that we just used, that we just defined. So let's do that. So instead of doing 2-property cache key here, we're going to remove this. And instead of doing all of this fancy work here, we're going to do something else. Namely, we're actually going to use this code and let the visitors handle everything else. And now we are passing also... Right. Because these two are done like one before and one after, I'm going to use peek instead of pop. And although I could pop before and assign it to something, there's various ways that I could do this. So this is -2. We're taking 2 steps back from our current position to get the check value, and then -1 with pop to get the previous one. And I'm just going to randomly do current pop. I could do this differently. I could do this better, but okay. This is what we're working with right now. And I can delete all of that code. And that's it. That's the implementation. Sorry it was so fast. I decided to do way too much stuff in this one, but I wanted to make sure that we got to some clear ending before we went on a longer break. I think that's everything. Let me just check my notes. Yeah, I think that's it. Let's see if it builds. No. And now the floor is open to questions. What's the difference between current arrow peak and current arrow pop? So what can I use? Here are our elements on the stack. If you peek -1, you just look at this element here. And you can do peek -2 and look at this element here. Pop is you take off the top element. That's the difference. Okay. Oh, good. I made spelling mistakes. Yes, those are lovely spelling mistakes. Okay, let's see. It's in mirror. There we go. I hope this works. Ah, and I made another mistake. Ha ha ha. So that'll break, so I'm just going to let it break. So one question is this a, oh no, that's not a question, that's a statement. Cool. Errors, errors, errors. Yep, that's it. And now we get to watch a lot of text scroll. I'm gonna see if there was anything that I missed in terms of questions. Oh, you know what I'm going to show you? I told you that I was going to show you what's going on in terms of the graphs when we move from mirror to Lear, and also what a graph looks like. And I actually have that all ready for you. So, what are we looking at here? Let me show you the function that this is based on. My computer's a little slow, so it's taking a minute. Here we are. Okay, so we've got this funny function. It doesn't do anything super interesting. But the first thing from line 1 to 3 is an error function. It returns a new error. Then we've got this test. It doesn't actually throw an error. I don't know why I called it throw error, but it returns an error object. We've got test that's doing something that's definitely not going to work. Then we've got a definition of something. So just pay attention that it's on line 4. On line 8, we have another function that's doing something sensible. And on line 14, we've got a for loop that's doing a bunch of stuff. So let's take a look at what the graph is for this whole thing. Here you'll notice that we're looking at well.js on line 4. This corresponds to that buggy code where we've got null, open brackets, and then stuff. And what this is the mirror node that with all of the instructions defined as an image. And you can just take a look at this and be like, okay, what is this doing? So we've got a parameter, this lot. There are no parameters here. We have a constant null, which is true. In the code, we had a constant null. I have no idea what this is doing, so I'm going to ignore it. It does a bunch of stuff that I think that this is the evaluation stuff to check if it is something doing something interesting, because all of this code is doing the check except for the last bit. This is all preparation code. That's what it's doing. And then we've got prepare set element. This is the opcode that we defined. And it's taking a box value and a type barrier value. And inside it's got a get property cache and barriers associated with that. And in the end, it calls set element on that and does stuff. I have difficulty reading this. Today was the first time that I looked at one of these. So this is what Mir sees. And it's already gone through 27 passes. So if I scroll all the way up to this thing, so like starting all the way here and just like keep going, what you see up here are the passes, the optimizing passes that we do. And you'll notice that because I didn't do any optimization work at all, the code's barely changing at all as we go through this. Right, okay, and then once we get to the 27th pass over the same code, now we're generating Lear, the lower level intermediate representation. And what gets interesting here is that we start talking about registers. So here, this V12 is a virtual register. We're not talking about physical registers yet. And then the next step that we do is we actually allocate the registers. That's the exact step that's happening here. And like, for example, one value is being allocated to RAX, another one is being allocated to RDX, another one is being allocated to RCX, etc. So this is the difference between the Lear representation, intermediate representation, and this is Lear, and the previous one was Mir. And on top of it, what we can do is we can see the graph of everything that's going on. So this is a representation of that whole for loop. And we can see how it changes over time as the different passes modify what's happening in the code. And yeah, that's basically it. I think it's super cool. So let's see if things have figured themselves out. Oh, it's still breaking. No member input of check object courseful. Did I do something really, really terrible? Yes, I did. Oh, how nice. Where was this? This is in code generator. And there we are. Renaming things. Do I have anything else that is doing something silly? I hope not. Ah, yes, there's one more thing that I'm doing silly, which is this is incorrect. We want to use this function, which we defined in our last stream. I hope that works. Okay, whew. Okay. So we're in open question time. You can ask anything that you're curious about, and I'll try to answer, while also trying to make this work, which it currently isn't. Let's see what else I did. That looks like it's a problem in Ion. Because probably I didn't delete something. Yeah. There we go. Prepare set LM, that looks good. Am I Russian? This is a philosophical question. I was born in Moscow, so in a sense, but I lived most of my life in Canada, and my Russian sounds, imagine a child from the 80s with a lisp. That's what I sound like when I speak Russian. There's a question as to if someone wants to learn how to write compilers, what should they read, and is the Dragon book still a good source? The Dragon book is a very complete source, but I wouldn't recommend it to learners. I would recommend something that isn't as dense. The Dragon book is extremely dense. It'll talk to you about stuff like type theory, and it'll tell you how to write an LALR compiler and various different types, not an LALR compiler, an LALR parser generator, and various other types of parsers. And it's going to get into how grammars work. And all of this stuff is very interesting, but it's overwhelming. So I would recommend something something that's more friendly to start. There's a really great paper that I don't remember the exact name of, but I can find it, where the author of the paper writes a compiler that's always in a working state. So that's similar to what I did with the Twitch compiler. That Twitch compiler is super small, and it gives you all of the information about how compilers work. I'll just share it here once more about how our compiler works, like high-level information. And we're not talking about machine code or anything like this, but it gives you the sense of what you can expect from an engine, and it has all of the pieces. So you have a lexer, which is just splitting things up into tokens. You have a parser. You have an interpreter. You have a thing that will create a script object, which is very similar to what we do in SpiderMonkey, that gives us a counter, a compiled script in the bytecode. That's what we pass around between the different layers of the compiler. And then we have the actual compiler. And this is like a super simplistic language that just prints duck, goose, swan, or finch. And there's a tiny grammar written for it. Just to give you a place to start, that's one place you can start. Someone also mentioned Crafting Interpreters. That's an excellent book as well. I would recommend that too. An incremental approach to compiler construction may be indeed that paper. Let me just take a look at if that's it. Yes, that's exactly the paper. The paper linked by Rabbit Pancakes is the paper I was referring to as a condensed look at how to build a compiler. Okay. We have a working implementation, theoretically, hopefully. Let's see if it works. So before, you might recall that we have these flags that we can say, build this only in baseline, or build this only with ion, or disable ion, or something like this. And what I can do is I can run the code with just with the ion level compilation. And I do it like this. The flag is ion eager, and we can just run that file that I showed you earlier, and it's totally broken. Fabulous. What did I do? Well, this is what we have. This is why we have a backup code. I'm just going to go to the backup code and we'll run it. Disappear all of my mistakes that I did while live coding. And this should work, so. What are the questions? I showed a PDF or something with all the compilation steps. How did I make the PDF? You mean the images of the graph? Is that the question? Because that's a really good question. Backup code. Yes, this is exactly like TV chef with pre-prepared cooking. That's exactly what I did. Okay, so the question about how to get those graphs. And the graphs we're talking about look like this. So there's a way to get all of this fancy information. Ian just posted a link to it, and I'm just going to copy that link and show you that thing. So this is instructions for how to spew out those graphs. And the important thing that you want is actually setting this ion flags to make sure that it has logs. And then there's a project called Ion Graph on GitHub, and it will generate those graphs for you. The way that you run it is you run SpiderMonkey with that flag, with this logs flag, but like you can use all of these flags and get more information. And then go into this repository and run make. And make, so there's a make script if you're a make file. If you're unfamiliar with make, you can just run make and it will run the first command, which is going to be all. So it will build a GV, which is graph viz, I think, and PNG and PDF. Or you can just do make PNG and you can just read these other things to understand what this make file is doing. What unfortunate animal is a spider monkey? So I don't know if you know the story of spider monkeys, of the naming of spider monkey, but spider monkeys are, the story goes that the name came from Brendan Eich because spider monkeys are so ugly. I think they're super cute, but his idea was it's ugly and it has these really long arms that get into everything, because SpiderMonkey used to be this this project that like went and stretched out into everything. That is the animal that this engine is named after. It is also one of the oldest JavaScript engines. It's not the oldest. The oldest engine came just before SpiderMonkey, and then SpiderMonkey followed it immediately. Yeah, so this is one of the oldest engines. You will find Brendan Eich code around as you traverse Searchbox, and sometimes that's a lot of fun. All right, and theoretically this is almost done. This is working. Let's let's make sure that it actually works. There we go. Hooray, and it's working. I made another small spelling mistake, but the steps were effectively the same. So if you want to replicate this, you can. And see it working for yourself, break it in various ways, and learn more about the engine. Unfortunately, we didn't get to go in and break the engine intentionally to learn more about what it was doing, because there are some interesting places where you can do the wrong thing and get some cool information about how the engine works. Like, for example, we can make this error message be wrong and learn about why it's wrong and stuff like that. I am gonna stop here. And I'm going to figure out a way to get you information about how to vote on what you want to see in 3 weeks. But one thing is going to be consistent. It will for sure be on this GitHub page. So just like what I'll do after this stream is I will add a link at the very top here of this repository. I'm going to post it to you all now. What you can do is you can tell me if you want to keep working on this bug in 3 weeks and do the optimizations, or if you want to switch to a new bug and start from the beginning again. Because all of these are going to be done in cycles, and that'll be a way for you to accumulate knowledge with repetition, so you'll get a more natural sense of how the engine works. All right, I think that's it. Are there any other questions? Can you watch the previous episodes somewhere? Yes, you can. And that I need to put somewhere more convenient. I'm just going to copy this over to you here. All of the streams will be captured in this guided tour series, and you'll be able to view them at your leisure without Twitch deleting them off of my channel. All right, I'm going to stop my stream here, and I'll be in the chat. So if you have further questions, I can chat with you and answer any of those questions going forward. And then beyond that, I will see you in 3 weeks, and I'm looking forward to where we pick up from going forward.